Howdy, folks. My name is Arul Verma, and this week in CS 128 Honors, we're going to be covering borrowing and ownership. Please excuse me, I have a sore throat, so if you hear me cough or pause a little bit, uh, just know that I'm a little bit sick, and bear with me, please. So let's start by talking about what ownership is and why it's important to us. So ownership is a memory management protection system using a system of rules checked at compile time. And that sounds like a lot of buzzwords, a lot of keywords, and it doesn't sound very helpful. So let's break it down. What does this mean? Well, ownership is a set of three primary rules. The first rule is that each value in Rust has an owner. The second rule is that there can only be a singular owner at any given time. And the third rule is that when an owner goes out of scope, the value will be freed. Below, we can see an example of what I mean by out of scope, or scope in general. Scope essentially refers to the curly braces that the variable is encased in. In this case, let s equals hello declares s inside the scope of these curly braces. That means that s exists and can be used in any way, shape, or form inside these curly braces. S is not valid prior to these curly braces or after these curly braces end. And the reason for that is basically how memory works. The way most languages handle memory is the moment these curly braces end, if a variable is declared inside here, the assumption is that because the variable is stopped being used outside of this braces, it is freed, it is released from memory. So the compiler no longer stores that data in memory, and therefore if you try and access it, you'll get an error. So that's what we mean by freeing memory. So that's one example of scope. We can see that scope in Rust doesn't actually work exactly like this. Scope in Rust has some more additional details in top of the details that we've already specified. So what Rust does for scope is not only does it check the curly braces that the variable is inside, but it also checks the last used point of that variable. And I'll explain why this works in a second. But first, let's look on the right here. In C++ or Java, if you were to talk about the scope of I1, you would say that the scope is in the entirety of main. It is within these curly braces, the larger of the two. And if you were to talk about the scope of I2, we would say it's the inner curly braces. It is only within these two curly braces. However, in Rust, the scope of I1 begins just prior to its usage, so this curly brace, and it goes out of scope right after it's declared. And the reason for that is because I1 is never used after this point. If there was some usage of I1 after this second curly brace set, then I1 would still be in scope inside these curly braces. However, at this point, I1 has gone out of scope and only I2 is in scope. And then we reach our second curly brace set where I2 goes out of scope. And at this point, nothing is in scope. So that's how Rust handles scope, which is slightly different compared to other programming languages. And the reason for this is because of something called non-lexical lifetimes. The way Rust handles compilation of code is slightly different. We touched on this briefly when we were talking about functions, but Rust essentially scans your entire code and converts all code into memory or MIPS code, essentially assembly language code, prior to actually executing anything, unlike any other language out there. Any common language you've used before, C++, Java, C, Python, they all require you to go in order, essentially, of code, and they don't scan for any form of scope or memory management. Java has its own garbage collection, C++ has pointers. So a lot of these don't really work in those languages just because of the nature of how their memory systems work. Rust can also do this entire scope thing because of the nature of ownership. Ownership inherently protects memory in a way such that it allows rules like these scopes to be defined. And the reason for that is primarily because of how pointers work and why pointers don't really work in Rust. So let's skip ahead a little bit and we'll revisit that slide. Essentially, in this piece of code here, if we were to, this is a piece of C++ code. Here we create a pointer to a string s2, and we say it's going to be a new string called hello. We say s3 is equal to s2, and then we delete s2. In this case, what's essentially happening is that this address at s2 is being deleted. So this address at s3 is also deleted. We still have the number, But inside this address, there's no longer any data to be stored. So when we try and see out the data that is stored at S3, we will essentially get a null, we'll get an error, because this data has already been deleted. And Rust inherently protects against this via ownership. What ownership essentially says is that S2 is the original owner, and then we say S3 is equal to S2. So now S3 becomes the owner and S2 goes out of scope. So this delete S2 automatically happens. There's no point in calling it. And this manual call of the delete S2 doesn't delete any data. It doesn't actually delete the string hello because S2 no longer has ownership over that string hello. It cannot access, it cannot deal with that data in any way, shape, or form. Only S3 can. So this line would break essentially, and the compiler would tell you that it's not possible. So that's how Rust protects memory management. And that's also why ownership is important to prevent this exact scenario, essentially. So now let's talk about why we need memory protection. We've kind of hinted at it with the example earlier, but essentially there are two types of memory, heap and stack memory. Stack memory is short-term memory. It's shorter in size, but faster to access. Data is usually automatically placed in the stack, and you don't have to allocate custom types of memory. This is an example of this is in any form of the data types we talked about earlier. Integers, floats, doubles, strings, characters, they're all placed in the stack, even lists. But heaps, their alternative, is long-term memory. They're larger in size and they're much slower to access. You must declare the amount of memory before you allocate per object, and you have to deallocate the memory in order to prevent memory from leaking. An example of this is anytime you use the keyword new in Java or C++. And what Java essentially does to handle memory is it doesn't let you access the stack or the heap directly. You can't access address locations or memory inside addresses. And because of that, there's no problems where you're ever double matching the same piece of data. There's no way to have two variables point to the same piece of data. So that's why we can inherently use something called garbage collection, where at runtime, a headless daemon thread, basically a thread that runs on its own, determines which memory is unused by essentially checking to make sure that it's never used again in the code, and then it automatically deletes those pieces of memory. With pointers and references, we've just seen why that's not possible. If we try and garbage collect S2, because S2 is never used again after this delete, we'd get a null. So we cannot actually have automated garbage collection. And ownership is the solution. The particular reason for this is something called borrowing. And I talked about it earlier. I wasn't super clear about it. This is a more visual example of what borrowing looks like. When data is on the heap, and when you borrow data from the heap, you can only have one owner. So the original owner gets immediately freed. We can see on the top, this is essentially what the C++ code was doing. It had an S1 and an S2, both of which are pointing to the same index 0 of hello. And this is what C++ does. And then we freed S1, and then this would not have anything to point to because this entire data was removed. But what Rust does is it doesn't let this happen. On the time that S2 borrows from S1, essentially when we do this S2 equals S1, this first table gets automatically deleted. It's removed from existence. So if you're trying to do print line hello world S1, this would immediately fail. And the compiler would catch that S1 has had its data borrowed, and we cannot access S1 because S1 is essentially out of scope at this point. So when does borrowing apply and when does borrowing not apply? So like all rules, there are always exceptions. Anything stored on the stack inherently has something called the copy trait. And that trait is what allows for equivalence operations to be used without borrowing. So a great example of this is like, why can we do int a equals b? And if we already declared b equals 5? Well, this is why, because integers already have a copy trait. And usually, most data types have copy traits implemented. And any data type that you've worked with, integers, booleans, floating points, characters, tuples, strings, anything of those, they all have the copy trait implemented. Vectors and arrays sometimes don't. So you have to be conscious of whether what you're using has the copy trait implemented or not. And if it does, you have to think about how you can go about copying that data or creating some sort of equivalent data, doing what we call it in programming a deep copy, in order to make sure you have two instances of the exact same data in different pieces of memory. So the alternative to something called copying is cloning. So what if we want both S1 and S2 as variables we can access? Deep copying or cloning is the answer to what we can do. Clone is a built-in function for all classes in Rust, which completely copies all data. And you can turn S1 into hello, and you can say S2 equals S1.clone, and we have identical data, and we have the same index, everything, but it's in a new piece of memory. So this is how it's done. You just use .clone. It's worth noting that not everything has clone implemented as well. It is a built-in function, but not for every piece of data type. So do check your documentation to make sure that clone is implemented. For almost everything you'll be doing in this course, clone is entirely usable and should be pre-made, but it is worth checking and asking if you're unable to use it. So what's the difference between cloning and copying then? We kind of talked about how you can have integers with just the inherent copy, and cloning is something that does essentially the same thing. Well, the difference is in how they work. Copying is what we call an implicit function call. And an implicit function call is something that you don't explicitly have to call, kind of like how we didn't have to explicitly declare our types. It was the implicit type declaration. What copy does is when you have an equal sign, it implicitly calls that copy function. And we use essentially memcopy. We just copy that memory over. This does mean that it can, for complex data types, like if you have tuples or say you custom make a class, you can unintentionally create a move or unintentionally cause a move and do something called a shadow copy or shallow copy, where all you're actually doing is you're copying certain pieces of data, but certain pieces of more complex data are not being copied properly. And this does not create a deep copy. So this is oftentimes very prone to error. I would not use it for anything that is not a basic data type that we went over in lectures 1 and 2. Clone, on the other hand, is an explicit function call. It's always a deep copy and it can do complex operations to create a new object. So if you have a vector, for example, clone would always clone each individual element in your vector before cloning the entire vector as well. So it would make sure that you would never encounter errors with this. But if you were to use copy, you could unintentionally run into errors. And you can see for vec, you have to explicitly use clone because if you try and use the equal sign, that would cause a move. So that's the basics of ownership and borrowing. As always, if you have any questions, feel free to reach out to us. And homework 2 has been extended because of the late release of this lecture. And follow along on the textbook. Uh, a lot of ownership and borrowing information can be found there. If you have any questions, feel free to reach out to us over Discord. Thank you so much, and looking forward to see you guys next week.